Good evening, grade 12s. I've uploaded the latest version of iOS 13 point I don't know what, and YouTube seems to have changed some of its formats. Anyway, it seems to be working again, but I lost one lecture. Anyway, this is your lecture for grade 12, day 34, period 4. The homework I gave you yesterday was page 602, practice example. So let's have a look at that. It asks, consider the following reaction. 2NO gas plus bromine gas, which is diatomic, gives you 2NOBr gas. A, write the rate law for the reaction assuming it involves a single elementary reaction. B, is a single step mechanism likely for this reaction? So because they say that it occurs as a single elementary reaction, we're able to write the rate law using the coefficients for the reactants in the equation as the reaction orders. But can you from there assume that it's a termolecular reaction? No, because termolecular reactions tend to be very rare. It's more likely a two-stepper with a fast step and a slow step, but it looks like one. And we'll see on the next practice examples where they show us how to deal with the reactions that have a slow step and a fast step. That's called the slow step being called the rate determining step. So termolecular reactions are highly unlikely because it's like having a car accident with 3 cars at the same time. It just doesn't happen with any sort of regularity. It's quite possible to have a 2-car accident which then causes a traffic disturbance which results in a 3rd car running into them, but very rarely are you going to get 3 cars colliding simultaneously. And it's the same with molecules. Molecules collide at astonishingly high rates in the quadrillions per second, if I'm not mistaken. But out of those quadrillions of collisions, only a small number of them are actually productive of chemical reactions. And sometimes, even though you might have what could be a productive collision, if the collision doesn't take place with sufficient energy, you still don't get a reaction. That's what we find out from looking at Arrhenius's work. Arrhenius came to the conclusion that temperature definitely had an effect on the rate of the reactions, and that obviously orientation of the molecules was essential to the achievement of the reaction as well. So the next thing we want to look at is the rate determining step for a multi-step mechanism. And what we call the rate determining step that comes up as an issue in such situations. So let's do that. Rate determining steps, you don't realize how many of them you get in your life. When you get stuck in a traffic jam, you are in the rate determining step. Somewhere ahead of you, there's a bottleneck. The cars are having to pass through an area that's slowing them down. Sometimes it can also be some kind of a phase reaction where a wave propagates through the traffic. I suppose if you were in a drone looking down, you'd be able to see it happening. But typically there's some kind of bottleneck. Something has slowed down and it creates a wave of slowed down cars, and once that starts to propagate, you get a traffic jam. Molecules that react, sometimes in multi-step mechanisms, you're not going to see that as an outside observer. You can't see the molecules reacting. You can see the final product, obviously, and if it's a multi-step synthesis, the rate of that synthesis is going to be directly related to the slowest step in the process. Let me just check to see that you're all with me. Or at least it's recording. Yes, it's recording. I've also changed the lighting. If you've noticed, I've put a work light that doesn't reflect off the board. It's less glare. So the overall rate, it's no small feat to set up the production of a video so that it doesn't look chintzy and cheap. And as you can tell, I'm not a a director of cinematography by any stretch. The overall rate of a reaction cannot exceed the rate of the slowest elementary step. Which is called the rate determining step. On practice example 605,
we did 602.
now you can sometimes have a slow initial step followed by a fast second step, and sometimes you can have a fast initial step followed by a slow second step. And they have slightly different looks to them.
Let's look at practice example on page 604. The question is titled, the sample exercise is titled Determining the Rate Law for a Multi-Step Mechanism. So on the practice exercise on page 605,
they ask the following question. Ozone reacts with nitrogen dioxide to produce dinitrogen pentoxide and oxygen. I'll show the equation, which I'm going to write in a minute. The reaction is believed to occur in 2 steps, and it shows the 2 steps. The experimental rate law is, and they give you the experimental rate law, what can you say about the relative rates of the 2 steps of the mechanisms? All right, let's write what it looks like. So here's the overall reaction. Ozone, O3, plus 2 nitrogen dioxide gas gives you dinitrogen pentoxide plus oxygen. And the reaction occurs in 2 steps. You start off with ozone, which bumps into nitrogen dioxide, and what you get is nitrogen trioxide plus oxygen gas. And then the second step is that nitrogen trioxide gas bumps into nitrogen dioxide gas to yield nitrogen pentoxide, also a gas. Now the rate law is this: rate is equal to K, rate constant, times the concentration of ozone times the concentration of nitrogen dioxide. What does that tell us about the rate determining step? The slowest step in that reaction is the one that occurs with these 2 reactants, and that is in the first step. First step. This is step 1. Step 1, this is overall, and step 2. So this is the slow step, and this is the fast step. But the slow step is the one that gives you the rate. Can't go faster than the slowest step, right? So the rate law is determined by the rate determining step, which is this one, and the first step is slow compared to the second step. Now, sometimes a 2-step reaction has a fast first step followed by a slow second step. The first step affects reaction rates by supplying one of the reactants to the second step, so it is necessary to state the concentration of this reactant in terms of the other reactants. So let me show you what that looks like. Eraser. Okay. Black eraser on a black chair. This little board's not too bad once you get used to it. So sometimes two-step reaction has fast first followed by slow second. On page 605 it says all that. Some reactions have fast first step and slow second. So that has an effect on the way the reaction devolves. The first step affects the reaction rates by supplying one of the reactants for the second step, so it is necessary to state the concentration of this reactant in terms of the other reactants. Thus, if A plus B yields AB in a reversible equilibrium where the forward reaction has rate constant K1 and the backward reaction has rate constant K to this -1, and we call that a fast step. That's the fast step. And then there's another step where the AB complex that's formed in the first step combined with something C, and that we'll call that K2, reaction constant 2, and you get ABC at the end. And this is a slow step. So if the rate of the reaction is given by this, K2 times AB concentration times C, since K sub -1 of AB is equal to K sub 1 of A times B, so at some point you get an equilibrium when this is going in both directions. Because this step is faster, some of this stuff will build up, and then some of it will start turning back into A plus B. At some point you get an equilibrium. They sometimes call it steady state, because some of this is getting used to form ABC, but because this is a slow step, it doesn't eat up all of the AB that gets formed by the fast step. So actually AB builds up. So you get a steady state happening where this reaches an equilibrium. That's what they're talking about here. When it's at that steady state, these two are going to be equal. The forward rate and the backward rates of this one will be equal. So what do we say? Let's find out the concentration of AB in terms of all the other things, because then we want to be able to feed it into this. So therefore we could say AB concentration is equal to K1 times A concentration times B concentration all over AB. And the rate of the reaction is going to be equal to K2, which is from this reaction times the concentration of A times C. But this whole thing, did I miss something there? I missed my K minus 1. No, this AB shouldn't be belonging here. Sorry, K to the minus 1 on the denominator. So this whole term can replace this. So if you substitute AB by that, then you can rewrite this equation with the AB substituted by this. So you're going to get K2 times K1 over K minus 1 times A times B times C. Sorry for the skinny writing, I'm just trying to avoid writing on my kitchen wall. And all these K values, because they're constant numbers, if you multiply a bunch of constant numbers, you'll get another number, which is a constant. So this is the observed rate constant. It's made up of these three different constants. So you can call it K observed. You can say K observed times A times B times C. Because you've substituted the AB that was here by this whole thing. And then because all these are, say it's 3, this is 4, this is 5, you can say 3 times 4 over 5, that's still a number. 12 over 5, you could put that as 12 over 5 over here, call that K ops. So the rate, oh, I'm using a capital R here. The rate equals K observed and I already said that K observed is equal to K2 times K1 over K to the minus 1. And I give you one example to do on page 607. I know that time's flying. Okay, where am I? So, on practice example, page 607, it says,
practice exercise. The first step of a mechanism involving the reaction of bromine is Br2 gas turning into two monatomic bromines, gas, fast equilibrium. What is the expression relating the concentration of Br gas to that of Br2 gas?
so here's the original equation. Br2 gas is reacting to form two Brs. And you're getting K sub 1 and K negative 1. So K1 Br is equal to Br squared times K to the negative 1. So K1 Br2 over K negative 1 is equal to Br squared. Therefore, Br concentration, if you take the square root of both sides, is going to equal to the square root of this whole thing. So it'll be K1 Br2 over K to the minus 1. The radical sign over, or raised to the 1/2 power. The last thing I want to teach you about is catalysis. So catalysis is when you speed up a reaction by introducing a substance that helps the reactants come together in solution with the appropriate orientation so that they can speed up, so that you achieve equilibrium more quickly. Biological catalysts are called enzymes. They're made up of a series of amino acids all strung one after another in a chain, and that chain tends to fold up into a three-dimensional shape, and then those three-dimensional shapes are specific for they're very specific for different reactions in your body. For example, there's an enzyme called trypsin. There's another one called chymotrypsin. There's other peptidases that are specific for cleaving groups of 2 or 3 amino acids. So each enzyme is very specific. If you're lacking one enzyme in your metabolism, it can have some pretty serious consequences. If, for example, if you suffer from a disease called alkaptonuria, you get a buildup of something called homogentic acid in your body because one enzyme in your body can't properly metabolize, I forget which substance, but the homogentic acid builds up in your urine. Your kidneys get rid of it, but your urine turns black as soon as it hits the air. It's a pretty freaky result. Your whole life, your urine turns black when it hits the air, but other than that, I don't know if it has any terrible effects on your health. I have a friend who has a galactosidase deficiency. One of his enzymes for metabolizing a specific sugar is defective, so he can't eat any cheese because it makes him violently ill and it damages various mechanisms in his body. I think it damaged his sight to some extent. So it can be it might seem like a very minor thing, but it can cause serious effects depending on what you eat. There are kids who are born with a substance called an inborn error of metabolism called phenylketonuria, where they can't metabolize phenylalanine, which is one of the amino acids that you find in proteins. There's 21 different amino acids, but if you get phenylalanine in your diet when you have phenylketonuria, it causes brain damage. So people who have phenylketonuria, they can't drink anything with, I think it's aspartame or one of these artificial sweeteners that has phenylalanine as one of the amino acids used to make the artificial sweetener. So, and it'll even say it on the cans, not for use, do not drink if you have PKU, phenylketonuria. So there are many things like that. Some of them can be very serious. Some of them might have mild outcomes. Some of them can cause a stillbirth. You know, if it's a serious place in the metabolism that's necessary to life, then the fetus will not be viable. Anyway, let me just show you, because you'll be able to read it, I think. Catalysis, a substance that speeds a reaction without being consumed, is a catalyst. Homogeneous catalysis, catalysis in the same phase as the reacting molecules. Heterogeneous catalysis, that's where a catalyst is in a different phase from the reactant molecules. And catalysts basically lower the energy required to achieve the transition state by favorable orientation of the reacting substances. Enzymes are biological catalysts composed of protein. They are very efficient at lowering the activation energy for the reactions they catalyze. Now let's give you a teensy weensy bit of homework. Try not to give a lot, but it's good to do with the little I give you. Let's do 1413. And I have a sneaking suspicion I gave you that already. And one more. Let's try 1422. Just those two questions, and then tomorrow we'll review it, and maybe I'll give you a mock test tomorrow. See how well you respond to that. Maybe you can ask me some questions in the comments if you feel like you're lost. You know, I'm happy to answer specific questions. Okay, we'll see how well this upload works.